All right, so here's the kind of the general plan. We've been talking about forces and Newton's laws. So what I want to emphasize to you is that when we talk about forces and Newton's laws, there's a whole bunch of things, a bunch of pieces that go into it. The biggest predictive piece has to do with Newton's second law, and we've talked about this. We haven't done all the details yet, but we talked about this. This conceptually says something that's pretty easy to visualize. Okay, what it says is that if you exert a larger overall force on an object, its acceleration will go up. If you have an object that's mass increases with the same overall force on it, its acceleration will go down. Right? So effectively what we're saying here is that acceleration is directly proportional to the overall force on an object and inversely proportional to the mass of an object. And where things get, so that's pretty straightforward. It's not that hard to understand. Where things get crazy really quickly is this side of the equation. This side of the equation is forces that are mathematically added together. And what we've done so far is we've looked at situations where we have like the simulation where we had the box, and you had one force here that was kind of a pushing force, and then there was another force in the opposite direction. And sometimes they were equal, so there was no net force, no sum of forces. And then there were times when your pushing force was stronger, so there was an overall force this way. There's times when the friction force was stronger, greater pushing force this way. And that's relatively straightforward. You don't have to do a whole lot of fancy math with that. We also did the same thing when we had our cart with the little block of wood in front of it, where in this case what was going on was there was a pulling force, right, from tension, and then friction was in the opposite direction. And this was a little bit more complicated because it's not a simulation, but what we did is we said, okay, wait. If we make sure that there's no acceleration, if acceleration is 0, then because of this equation, if the acceleration is 0, the sum of forces has to be 0. That means these two things have to be equal to each other. So the force of friction is equal to the tension in the strain. We used the force sensor in the supercarts to measure the tension, and we either used the we used the motion capability of those supercarts to determine that we had 0 acceleration, which is pretty easy to figure out what the force of friction acting on those carts was. We did that with a bunch of things. We did that in a bunch of different ways, but essentially what we were doing is we were using Newton's second law to figure some stuff out. Where it starts to get crazy is when we start thinking about some additional mathematical complications. For example, we might have an object that's experiencing one force in this direction, one force in this direction, one force in this direction, and there's some sort of overall acceleration. And, you can't accelerate in more than one direction at once, so maybe it's accelerating this way. Based on that, we would need to figure out, what are the various forces involved, or what's the mass of the object? And all of those things involve a degree of vector mathematics that we haven't really hit yet, but we're going to. Another piece that is pretty complicated that we've been dealing with is this piece right here. The force of friction is one of those things where, this is a force, right? In this case it's pushing on this box this way, in this case it's pulling on this cart this way, and so it's a force. Forces are pushes or pulls, and they have some sort of size, and we measure their size in newtons. But we've been working with friction for a while, and one of the things that's become apparent is that friction is super complicated. It's different if the object is motionless, if it's at rest, if it's still, versus moving. And it is, to a certain degree, unpredictable, because even if the object is still, that doesn't tell us what the force of friction is, right? Like if I look at this block on this ramp right now, it's not moving. Is there friction acting on it? I mean, it's a little hard to tell, right? Like if I were to put a different cart with wheels on there, I don't know that there's any friction on this cart right now. Like it's not going anywhere, but it's motionless, not because there's friction, but because the ramp is pretty level. But as I start lifting the ramp up, we can see the cart starts to move. The block doesn't. So now there's friction acting on the block. And as I raise it, we figured out, we used like some math and we figured out well, the force of friction must be increasing. So when we talk about an object that's motionless, the frictional force isn't just one number. It's like, it can vary. Whereas when it's moving, do you remember when we used the simulation and you pushed the block and you pushed it at 125 newtons, friction pushed back with 125. Then you pushed it at 126 and friction dropped to 94. And then you kept pushing with more and more and more force and friction stayed at 94. So if it's moving, it's always the same. So if it's motionless, we don't even necessarily know what direction it's in, right? Like right now, I don't think there's any friction at all. If I tilt this end up, now I know there's friction opposing where this thing would be going. But if I tilt it the other way, now friction is in the opposite direction. So looking at a motionless object may not tell us what direction friction is acting. Friction is pretty complicated. There's another complication here as well. And that is that, and we're gonna talk about this today, but there's one other kind of there's one other kind of force that's really confusing like that. And those are normal forces. And the thing about normal forces is, in general, we really want them to just relate to the weight of an object. So for those of you who don't remember, normal force is a force from a surface that is pushing perpendicularly on an object that's on that surface. So if we look at this object right here, it's got a normal force acting on it from the ramp. The ramp is pushing up on this block. Pushing straight up because the ramp is pretty level. If I tilt the ramp, the normal force tilts. Right? The normal force is always perpendicular to the surface, so we kind of tilt it. And most of us can sort of intuit that in this case the normal force is the weight, right? Like if this thing is being pulled down by gravity, its weight is 25 newtons, then the track, the ramp must be pushing up with 25 newtons. It doesn't make sense that it's anything but that. As we start tilting it, it's a little bit less obvious. Because I would think, like, I'd be like, well, it's still the weight, but it's actually not. And we talked about that a little bit the other day, just kind of, like, there's been some inferences. But basically what happens is that it's not just related to the weight of the thing, but it's related to the angle of the ramp too. The normal force drops as the angle goes up, and you'll see that today, you'll see some of that today. But it gets even weirder than that. And let me give you a couple of examples. So here is this box right here is a force plate. It measures weight. And in fact, we can measure weight in pounds so that it makes a little bit more sense to you. So basically I have the track is being supported by the force plate. So it looks like the track weighs about 4 pounds, right? If I lift the track off of it, then it goes down to 0. And that makes sense. Put the track back on it, it's about 4 pounds. If I were to get on there, which you'll see in a minute, then we would be able to see my weight, right? So here's what's interesting though. There's a normal force involved here, right? The normal force is like the force from the force plate that's pushing straight up on the ramp. And so I would say, like, wouldn't you say the weight of the ramp is about 4 pounds? Because that's what I would say. But watch what happens if I tilt the ramp. The normal force doesn't change direction because the surface supporting this ramp is still perpendicular, right? Or the surface is parallel to the ramp. The normal force is still straight up. The normal force is still perfectly perpendicular to the ramp. Well, watch what happens as I tilt this up.
Okay. Oh.
Right? You see what's going on? It's increasing. The weight of this thing isn't increasing. The angle of the surface isn't increasing, but somehow the normal force is going up. And that seems weird. Yeah?
Just because the weight's being essentially halved by another support?
Yeah, so yes, that is effectively what we're doing, but if this device doesn't tell us the weight of an object, then what does it tell us? Because I want this to be the weight of the object. And here's another thing that's kind of weird, all right? So let's take a look at my weight. And so I should, my age, for my biological sex, for my height, I should probably weigh like, with my clothes and stuff, maybe 150 to 155, all right? So let's see how I'm doing. I mean, I'm 54 years old. Like, that's not too shabby. But we could do better, couldn't we? I think, and I'm not like, we're not gonna talk about like body dysmorphia or anything like that, but just realistically, like, sometimes it's worthwhile to kind of think about your physical health. And so I need to lose some weight. I think I need to lose some weight. And I need to do it right now. So Kelsey, can you come up here, please? Just stand right here. Micah, can you come up here and just stand right here, please? We're gonna put me on a diet. I think I need to lose between 10 and 15 pounds. Okay, so I'm gonna hold my arms out like this, and I want you guys to just gently push up on my arms. You don't have to push very hard.
What?
Oh, there we go. Now I'm looking good. That was like a 20-pound drop in about 30 seconds. Thanks, you can sit down. We should market this. And we've got, right? Like we've got a way to make some money. But actually that's all great. But I actually have a better way of losing some weight really fast. What I'm gonna do is I'm just gonna put the scale here, all right? And so now, oh man, probably that's dangerously underweight. Let's see, I can gain a little bit of weight here. There we go. Now I'm a feisty 20 pounds. So the issue here is that this scale is clearly not telling us weight. What it's telling us is force. And we generally, in physics, measure forces in newtons. So we think it's a little bit easier for us to kind of tease this out when it's in newtons, because we associate weight in pounds. But pounds is really just a measurement of force, just like newtons are. So when we think about the information that we get from a measuring device, there's two things that go into it that are really important. One has to do with these normal forces, which are more complicated than simply, oh, it's the weight of the object. The other is, what is weight, and what information do we get from a scale or some sort of measuring device? So we're gonna do two things today. The first thing, I'm gonna yak at you about friction, and we're gonna look in particular at this idea of like, how can we use what we've done so far to think about the forces that are acting on an object in order to make predictions. And then you're gonna start looking at this next piece, thinking about weight, normal forces, and the measuring devices that we use to determine those kinds of things. And so I'm gonna start by talking about friction, And there's a couple things here that we've already gone through. So I'm gonna go through some of it a little bit more quickly, and some of it a little bit more slowly. And I don't know how to make that. I mean, there's like this weirdness with this new board that I haven't quite figured out. All right, so the big skill here is what I just described to you. The big skill is that with real situations, like if you have a cart accelerating along a ramp, can you incorporate friction into any predictions that you might need to make with that? That's the big skill. How well can you use everything that we've talked about with friction to make predictions involving Newton's second law? Determine unknown masses, or make predictions about what an object's acceleration will be. Those are the kinds of things that we're going to be doing. And then if you kind of break that down and think about, well, like what are the sorts of things you can do when you can do this well? One thing is that you should be able to pretty easily move back and forth between the idea of friction being this really complicated thing that we don't know the direction of friction all the time. Sometimes the amount of friction can vary. Sometimes the amount of friction is constant. You can switch between thinking about friction as a really complicated thing and thinking about it as just a force in Newton's second law. That's what we did when we found the force of friction acting on the cart with the block in front of it. We figured out how much friction was involved. We didn't use any fancy equations. We just thought of it as a force, and it was unknown, and we figured out what it was. Another piece to this is a purely theoretical piece. This is not actually 100% true outside of theory, but it's reasonably accurate for a wide variety of circumstances. And that's the idea that really the only thing that determines the amount of friction between two objects is the surfaces themselves, how kind of sticky they are, relative to each other, and the degree to which they're kind of being squished down. And what we'll see is the surfaces, the stickiness of the surfaces is quantified by something called the coefficient of friction. We can just think of it as the stickiness, but the name is the friction coefficient. And the force squishing two things together is the normal force. We'll see that as well. Okay. And then the last piece is something that one of the things that happens is that if you start with the assumption that there is an equation for friction, you can work yourself into circles, because you're like, well, I need to know friction. This is the friction equation. I don't know this, and I don't know this. To find those, I need to find the force of friction. And to find the force of friction, I need to use the friction equation. And you get lost in this endless circle. But really, there isn't an equation for friction. There are lots of equations that have friction in them, which means if you don't know friction and you need to know it, there's a bunch of different ways that we can find it, because there's a bunch of different equations that will have that variable in it. It's kind of like kinematics. We've got 3 different equations that we can work with that all have initial velocity in them. There isn't an equation for initial velocity. There's a bunch of equations that have initial velocity in them. We talked about 2 of the kinds of friction already. The first is static friction. This is the friction that you get when an object is motionless. So if I put the block on the ramp and it's not moving, it is experiencing static friction. And we'll dive into this in a little bit more detail momentarily. This convention for the variable is not, there's no set or fixed convention. People will use lots of different things. You'll see lots of different abbreviations for this. Capital F generally means force. Lowercase f generally means friction. Lowercase f or a capital F with a lowercase f and a lowercase s generally means static friction. So a lot of times you get information in the variables, but a lot of times you just have to know what the situation is. If somebody tells you there's a block sitting motionless on a ramp, and then you start talking about friction, you have to know it's static friction, because it's not moving, it's motionless. The next kind of friction, and we looked at this as well, is called kinetic friction. And kinetic friction is, the same variable, capital F for force, little f for friction, and then K for kinetic. And this is the friction that opposes the motion of an object as it slides. So it's moving, okay? And this is a sliding force. And some of you are probably thinking, wait, what about the carts? We talked about friction for the carts, but they're not sliding, they're rolling. And you're right, and the thing about that is that we have a third kind of friction, which is called rolling friction. This isn't the same as kinetic friction. Rolling friction has some elements of kinetic friction, it has some elements of static friction, and it has some elements of things that aren't friction at all. I'm gonna talk to you about this for 30 seconds, kind of present it to you, and then we're gonna just lump rolling friction together with kinetic friction. It isn't the same, doesn't work exactly the same, but it's so close that we're just gonna pretend that when things roll, they're sliding, and we'll call it good. All three of these kinds of friction have in common that there is going to be a quantity associated with them, and I mentioned this quantity before. It's called the coefficient of friction. This coefficient of friction has a funny variable. It's a Greek variable. This right here is the Greek letter mu. And so this is how it shows up when I type it on my presentations. I tend to write it more like this. So it's like a sort of a funny cursive U or a funny capital M, and it looks a little weird, so get used to it. Sometimes we'll have mu with a little s or a k or an r to indicate that we're talking about the coefficients of static or kinetic or rolling friction. And the coefficients of these different kinds of friction aren't the same. So in any one object, any one set of surfaces, like this block on this track, it has one mu for when it's motionless and a different mu for when it starts to slide. So they're you can see we start to add pieces to this puzzle right away that can get kind of confusing. All three of these frictions oppose motion or potential motion. Okay, all three of these could be considered just a force acting on an object. Like in this case, we have an object that's sliding along a surface. We are shown in this diagram that there's some force to the right, don't know where it's coming from, and that friction is in the opposite direction. So it's a force. Static friction, we looked at most in depth when we were looking at the investigating friction activity. Static friction is what kept the block from moving. Static friction is weird because you don't know if it's there or not. You can't see, this block isn't moving, it's still not moving, it's still not moving. How do we know anything about static friction? And the answer is, we often just sort of have to tease it out. We have to sort of think our way through a particular scenario. What static friction does is it prevents an object from sliding. And so if we think about preventing an object from sliding, you'll realize pretty quickly that it can vary. It has to be able to vary. Because if something is preventing this block from sliding, and we change other forces on the block, like by tilting the ramp, and it still doesn't slide, then whatever was preventing it from sliding must have changed as well. If I walk over to this file cabinet and I pull on it, and it doesn't move, friction is preventing it from moving. If I pull with a larger force and it still doesn't move, friction must still be opposing the motion. If you see an object motionless on a ramp like this, is going to be your inclination is going to be to think that friction is preventing it from sliding down. But that's not necessarily true. If we were to think about this block right here, for example, the way it's depicted, a block motionless on a ramp like this with no other forces, then yeah, friction is going to oppose the direction that the block would go if we switched friction off, at which point it would start to slide down the ramp. But what if somebody else started pushing on this? What if this were like a piano and somebody else started pushing that object up the ramp? What you would see with the friction force is it would get smaller and smaller and smaller. There would be a point at which what was keeping this object motionless was not friction, but entirely this applied force. At that point, if friction were switched off, the object would still remain motionless. And then, if this person continues to push with more and more and more force, friction will change direction. Now, if we turn friction off, this object would start to accelerate up the ramp. That's weird to think about when we look at a drawing like this, because we don't see all that stuff interact. But in practice, we do stuff like that all the time. Like we push things up ramps. It's, in that case, if we're sliding an object up a ramp, friction is opposing the object's motion. Friction, in that case, is down the ramp, not up the ramp. We know that we can only get to some maximum size when we talk about this mysterious changing static friction force. And we know that because if this force could continue to grow, we could never get an object to accelerate. So it has to max out at some point. And the point at which it maxes out is the point at which the object starts to move. So we can increase the friction on this block by tilting our ramp. But once we get to a certain point, the force of static friction is no longer sufficient to hold it in place. And it's maxed out. It's as much as we can get. We also know, and this is where things are going to start to get really complicated when we deal with friction, is that it's not just a force that would cause an object to move, but it could be multiple forces that could cause an object to move. So for example, if I come and pull on my cabinet, and it doesn't move, then we know friction must be pulling in the opposite direction with the same size force. Well, what if I pull on it and somebody else does too? Now friction has got those two forces to overcome. If we're pulling in the same direction, and friction is in the opposite direction, well, what if I pull it this way and somebody else came over to this side and kind of pulled it this way? Now we've got two forces in different directions with different sizes, still not moving. There's only one force that's keeping it from accelerating, and that's friction. So in addition to the force of static friction varying with some other force, it actually varies with the combined force, all the other applied forces on an object in the plane of motion. So that can get really complicated. My goal is not to give you overly complicated situations, but the reality is sometimes it's complicated. When we look at what determines the force of static friction, the theory is the same as it is for all forces of friction. So one piece of it is that it's related to the surfaces themselves. This is the stickiness of the surfaces, and that variable mu is how we quantify it. The other piece is the force between the surfaces. The harder they're being squished against each other, the more friction we'll have. When you guys were doing the investigating friction activity, that compressing force was somehow related to the mass. You saw that, right? You added mass and it increased friction. But it actually turns out that the force that's causing this compression between the objects is the normal force, which is only sometimes related to the weight. And the relationship that explains how friction relates to the stickiness and the force pushing two things together is this right here for static friction. The force of static friction can vary. It might be less than, but it will never be more than this stickiness coefficient times the normal force. So this is not the friction equation. This is an equation that has friction in it. And this explains the two things that cause friction. One is how sticky the surfaces are. The other is how tightly they're pushed together. Stickier surfaces will have greater friction. Surfaces that are more tightly pushed together will experience greater friction. A lot of times when we talk about static friction, we want to know, well, what's the most? What's the largest force of friction? And that would be this. The largest force of static friction is going to be equal to our stickiness coefficient times the force holding two things together. You can't exceed that. That's the most that static friction can produce. So this can get really complicated quickly, or we can keep it simple. In this class, we're gonna see sometimes where it can be either, or both. If you think about this piece right here, we can decrease friction by decreasing the force between surfaces, which has to do with the normal force. Then I would argue that I should be able to decrease the amount of friction acting on this filing cabinet by pulling up on it, right? If I pull straight out, then the amount of friction acting on this at most is going to be equal to whatever the stickiness coefficient is times whatever the normal force is from the floor up onto this cabinet. But if I pull up on the cabinet a little bit, I'm decreasing the normal force. Just like when I lift up on an object that's on a scale, I decrease the normal force. So if I pull up on this, I can slide it more easily. That's why when we slide things, we do push or pull up on them. It's easier. You pull up a little bit, you reduce friction. It makes it easier to accelerate in the direction that you want it to go. All right, the next kind of friction, we looked at this as well. This is what we looked at when we had the cart with the block of wood in front of it on the track and we were measuring the friction. We also looked at this in the simulation. We looked at static and kinetic friction in the simulation. So kinetic friction is operating on an object that's sliding. And one of the things about kinetic friction is, unlike static friction, it doesn't change. Once an object is moving, unless you change the surfaces themselves or the normal force, the force that's pushing those two surfaces together, you won't change the force of friction. You can pull it with more force or less force. You can move it faster, you can move it slower. The force of friction will stay the same. So what we see when we start with an object that's not moving, if we start applying force to that object, what we'll see is the friction will go up for a while, and that's static friction. And then once it starts to move, it drops and becomes constant. This graph right here, this is the theoretical version of it. This is real data. I didn't collect this, this was from the internet, but you can see this, there's no applied force here. And then as the force starts to become applied, the friction force jumps up and then drops way down and then becomes constant. Okay? So it's not a perfect match for the theory, but it's pretty darn good. And the kinetic friction force is always going to be at least a little bit less than the maximum force of static friction. And that's because if it were the same, then the object wouldn't be able to move. If you are pushing on it and a force opposes your pushing force with the same size, then it will never start to accelerate. So we know that when you kind of max out static friction, that force of friction has to drop at least a little bit, so that, because otherwise the object wouldn't ever start to accelerate in the direction of motion. Theoretically, kinetic friction could be the same as the maximum force of static friction, but in practice it's always at least a little bit less, and sometimes it's quite a bit less. And then as with static friction, there's only two things that matter. Those two things are the stickiness, which is our mu, the coefficient of kinetic friction, and the force pushing the two objects together, which is the normal force. In this case, it's equal to that. There is no less than in this particular relationship, because the force of kinetic friction is always constant. but it's the same two things. What changes is this. Mu, the coefficient of kinetic friction, is less than, typically, the mu of static friction. You get more friction when it's not moving. You get less friction once it starts moving. Okay? The last kind of friction, I'm going to go through real quick because it's interesting to think about, but this is not something specifically you need to know. Rolling friction combines a whole bunch of things. There is kinetic friction in rolling friction. The axles and the bearings are sliding against each other as something rolls. There's static friction involved with rolling friction, because if you have a wheel that is in contact with a surface and that wheel rotates without sliding, then there's friction between the edge of the wheel and the surface. But since there's no sliding, it's static, not kinetic friction. And then there's a bunch of other things that aren't frictional forces at all. It's not related to friction. It's actually like pushing and pulling contact forces that occur from one object that's kind of in the way of another object. And basically what happens with rolling resistance, in addition to the kinetic friction of the axles and the bearings, the static friction present at the edge of the wheel, you also get this deformation. And it works in two ways. The first way is the surface that's being rolled on kind of bulges up in front of the wheel. And so it's pushing back from that bulge. The second thing that happens is the wheel itself deforms a little bit, it kind of flattens out. And so you have these like anti-rolling forces, like you can't roll a square. And that's kind of what we've got going on. The bottom of a wheel is always a little bit flatter. And when you combine those two things, you end up with an overall force from deformation in the opposite direction of the motion of the object. Combine that with the actual friction that's involved, and you get what's called rolling resistance. We sometimes think of it as rolling friction, but in this class, we're gonna lump it all together. We're gonna just say, anytime something's moving, it's experiencing kinetic friction, and that's as good as we're gonna get. And so the relationship between the friction of an object, the stickiness of the surfaces, and the force squeezing them together is the same for rolling friction as it is for kinetic and static friction. But we won't have to worry about using this relationship because we're never going to use the coefficient of rolling friction.
Do you use no rolling friction for AD?
No. When you work with friction, so like now we've got all this stuff, and so one of the things that happens is people think about, oh, jeepers, what do I do now? Like if I got a problem with friction in it, what do I do? Is it mu k? Is it mu s? Is it, what is it? And the answer is, the easiest thing to do is just remember that friction is a force. So when you make a free body diagram, it'll go on your free body diagram. How do you know if it's static or kinetic? Well, you need to think about if it's moving or not moving, right? It's going to be static friction if the object is motionless. It'll be kinetic friction if the object is moving. And we need to think about direction. When I talked to you about static friction earlier, I pointed out that you can't just assume that friction is always opposing gravity, because there might be other forces. But if you know enough about a situation, you can usually determine the direction of friction. If it's moving, it's in the opposite of the direction of motion. If it's not moving, you kind of have to, like, you might have to do a little bit of thinking, and sometimes you have to do some math to figure out what direction friction is in. But ultimately, we can put it all together in a free body diagram, and then it's possible that we might need to use those additional equations. We might need to use those additional equations to find the force of friction if we have enough information. If you tell me the coefficient of static friction, and you tell me the normal force between this block and the ramp, I can tell you how much friction is acting on it. And then I can use that in a free body diagram, and I could use that in Newton's second law. Sometimes we know what the force of friction is. It's 1.2 newtons. That's what we found, for example, when we were using the supercarts with the block of wood in front of them. As they got pulled along the track, we figured out what the force of friction was. We never thought about mu, or the normal force. We just figured out the force of friction by using Newton's second law and a little deductive reasoning. Well, if we then determined what the normal force was, we could find mu. We could find the coefficient of friction between two surfaces, and that might be really handy. So, so the equation with mu and the normal force in it is not necessarily required, but sometimes it's really helpful. And it all will hinge on your ability to accurately draw a free body diagram. If you can draw a free body diagram incorporating friction, then you're going to have a fighting chance of being able to use Newton's second law to figure stuff out. So these 2 points kind of go together. Like we have an equation that we might use, or we might not use. We might not need to know anything about mu or the normal force. What I'm showing you is not a friction equation. It's not the equation for friction. It's a model for friction. And what that model says is that the force of friction on an object will be related to the stickiness of the surfaces and how hard those forces, or how hard those objects are being pushed together. That's it. Surface area doesn't matter. The material doesn't matter except as it determines the stickiness. And the normal force will matter, but as we'll start to look at today, the normal force is not always going to be the same as or related to the weight of an object. So we're going to shift gears here, and I'm going to have you start looking at this what does the scale say activity. We started it the other day, and before I let you all attack it, I just want to show you really quickly how these things should be set up. Because one of the things that's happening, and I don't think it's you, I don't know who it is, but I've already gotten 3 force sensors that have been broken. Because what people are doing is they're looking at this L-shaped bracket on here, and they're like, I want that to be like this. And they're taking it and they're just bending it. And if you bend this bracket, you're not going to bend it, you're not going to break it, you're going to break the force sensor. And that's what they're doing. People have taken this and just torqued it. So don't make any adjustments to this L-shaped bracket. I put them on there, and I put them on there the right way. And if you use them the way that I put them on there, then what you can do is you can hook them on with one of these 45-degree angled brackets, and then you can rotate the force sensor like this to get different angles. So ultimately what you're going to be doing is you're going to be placing masses on the metal bracket like this, and then you're going to rotate the metal bracket like this. So nothing bends, nothing breaks, we're rotating about the metal pole, not about the L-shaped bracket that's attached to these things. If you find that your bracket isn't working, you can't figure out how to do it, it's loose, it's not attached right, will you come up here and you can either bring me your force sensor and I'll attach it correctly, or you can, I'll go back there and I'll fix it. But don't try to fix it yourself, because that's how they're getting broken. And the big question here is coming back to this idea of normal forces and weight, and what do these devices